Hey guys, welcome back to AI for Teens. This is my second video, and today I'll be talking about the MNIST dataset. The MNIST dataset is a really popular dataset that's used all over the world. Yes, even professionals use it. So I'm really excited to teach you guys about this today. Okay, the MNIST dataset overview. The amount of images this dataset has for training is 60,000 training images, and they have 10,000 testing images. The images in this data set are handwritten, but they look are like they're really pixelated. So it's like they look like tiny squares, and it's really like you can easily tell that this number right here is the number 8. But for AI, they see like these little tiny squares like these, and it's like really hard for it to piece together. So we just train the model to get it to work and to get it to know and understand what number it is. So the pixelated image looks kind of like this, and the resolution is the amount of pixels in the column times the amount of pixels in the row, which in this case, for the MNIST dataset, would be a 28 by 28 pixel. So this is kind of hard to understand, so let me just break it down for you. The 28 by 28 pixel, so there's different types of pixels, like there's different numbers of pixels, and here it has 28 pixels, so it has 28. A pixel is like the tiny squares, so I'm just gonna leave that out for you just in case if you guys are still confused. It's really hard writing with this. So it's a 28 by 28 pixel. So that's basically what the resolution is. So it's a 28 by 28 pixel. And the more images or the more pixels that you have, the more clear and the more better um the image will look, since it's going to be more clear and easy to understand. Train image classifier on MNIST dataset. Training, I did this training on a GPU. Um, The model details are simple neural network. I didn't do anything so complicated. I just used a simple neural network. And those neural networks, there were only two layers. Those two layers were the input layer and the output layer. We didn't need a hidden layer because the images are, I think, not that complicated to understand. And they just, they're just numbers. And AI is very good with numbers. Their favorite thing is numbers. So there was only two layers, but if you get more complicated images, there's probably going to be more input or more hidden layers. But in this case, they only needed two, which was the input layer and the output layer. So I just did all that work. The model got trained on 50 epochs. The epochs, like I said in the previous video, was the unit the of getting the AI trained. So the more epochs you train it on, the more accurate your model will be. So I just trained it on 50, and the dropout rate is 0.2. I'll be getting to on the next slide what a dropout rate is and what a learning rate is. And as I mentioned earlier, the training data set has 60,000 training images, and the testing data set has 10,000 testing images. So the ratio is 6 to 1. Okay. Dropout rate and learning rate. So, what is a dropout rate? A dropout rate is the fraction of neurons that are dropped. Let's take an example. When you're training your model, your code is saying that dropout is equal to zero point 0.5 or whatever format you wrote your code in. So that means if you convert zero point 0.5 into percentage, it would be 50%. So 50% of the neurons are not important or they are disabled, so we don't really need them. Like, I think I also mentioned this in my last video, saying that whatever pixels are not important, they're like, it's all based off of numbers. So if the AI sees that one pixel is zero point 0.0, then they know that's not important. So in this case, that means 50% of the neurons are not important. The learning rate determines the step size of each iteration. If you don't know what an iteration means, it's like the weights within a neuron that are getting like executed, you know? And at each iteration while moving toward a minimum loss of the loss function. So maybe in math form, you might be thinking that learning rate is also 50% due to the math to become 100%. I mean, lots of people would think that, but it just determines the step size of each iteration, the weights and the neurons. So, yeah. Okay. Training and test data split. Okay. So here, this is what I meant by the ratio. So, when I mentioned 60,000 training images and 10,000 testing images, the ratio is 6 to 1. So, this is what I meant. So, training the data. This is the portion of the data set used to train the model. Let's take an example of a test. When you're studying for a test, let's say math test, you get these questions, you start writing, and you start solving them. But in the test, you're not going to get the same questions, but somehow practicing still helps you get correct answers because it's the same term. Similarly, with training data and test data, the training images are used to train the model. It learns the patterns, relationships, and features from the data, and it updates its internal parameters like the weights in a neural network based on the set. Then, once it's giving the test, the portion is used to judge the model after training, and it contains data the model has never seen before. Like you're practicing, you see one question, like I'm going to take an easy example. What's 1 plus 1? 2, but on the test you see what's 3 plus 3, but you get how to do it. And it helps you measure how well the model simplifies to new and unseen data. So this is just the code I've I used to um, get the final results, which you'll be seeing in final slides. It's very, very cool. So if you want, you can screenshot this right now. And there's a lot going on in the code. It's it's very complicated to look at, but once you understand it, it's very easy. And there also is a part two right here. Okay, now these are the results of the code. So the training loss and the accuracy is 98.05%, which is really good for just 50 epochs. So as you noticed, at first it was very, very unstable. It just didn't know. But as the more epochs I trained it on, the more consistent it was with its results. And if you even go to 1,000 epochs, you might even see a straight line. This is just proving the point that the more epochs you train it on, the more accurate your model will be. Okay, now let's look at the inference results. So I created the load and predict.py. That was the name of my terminal. And I inputted this image right here. It's a 5. So I gave it this as my testing model, the 5. All right, but we also gave a 5 in training. So how are they different images? Like I mentioned earlier, there's lots of different there's lots of different ways that people write. The handwriting is very different. So some people can write their fives like this, or some people can write their fives like this, or some people can write their fives like this, or there's many different ways. So let's say in the training data we gave it this, but in the testing we gave it that. So it's clearly not the same way, but it somehow just pieces it together. The neural network just somehow pieces it together to understand that it's a 5. And that's really cool. So this is the image it gave after I trained it and it detected it was a 5, like it says predicted 5 over there. And this is how it looked like in the code. Predicted digit 5. So I find that very cool to see how the AI can actually do all of this and can lead to the final result. And that's it for today. Um, Thanks for watching my video. I hope you have a bit more knowledge about what MNIST dataset is, and I hope you will definitely use it in the future. Make sure to like and subscribe, and I'll see you guys next week. Bye.